Okay, in this module, you're going to get introduced to algorithms, the efficiency of algorithms. So we're going to analyze the runtime complexity. Okay. Uh, so what's an algorithm? An algorithm is basically a sequence of instructions that you execute to solve a particular problem. Okay, so for example, you want to compute the maximum element in a given list. You have a particular logic and you execute that logic as a sequence of instructions. Okay. So for example, you would have to first get the array, input array, and have the first element as your temporary maximum, and compare that with every other integer in the list. And whenever you find something greater than what you know as the current maximum, you update that new maximum, the maximum to be the new integer that you see to be larger than what you know currently as the maximum. And you keep on going to the end of the array, and whatever is the value of the integer in the that you know as the maximum, you output as the final output. So this is a sequence of instructions, and that you execute on a particular input. Now, the instructions should be non-ambiguous, and the output should also be non-ambiguous. So, for example, that means for a given input, you should get a particular output anytime, every time you execute the algorithm. Okay? And also, from a performance point of view, you should also specify for which kind of inputs your algorithm should work. For example, if you're expecting to find the maximum integer in an array, then the input should be a sequence of integers, not like characters or anything like that. Okay. And also you should understand that for a particular problem, there may be more than one way to solve it. Okay, that's what we'll eventually see in this course, and we could sometimes even compare the different ways to solve a problem. So the ways and things like that, what I mean is actually the algorithm. So for a particular problem, you may have more than one algorithmic strategy or the approach or the logic to solve it. Okay, and some may take less time, some may take more time, and so on. Okay, so that's what you would eventually end up be able to analyze the time complexity. So the course will essentially focus on taking a particular problem, coming up with the logic to solve the problem, and then trying to analyze how long it would take, first theoretically, to run the algorithm on a given set of inputs, and see if that time complexity is acceptable or we need to improve anything in the algorithm. Okay? And also we need to worry about the space complexity in the sense that it's not just sufficient to come up with a very time efficient algorithm. You might have heard of merge sort from your data structures class, where it's a very time efficient n log n algorithm, but it requires an additional order of n, state of n space, actually, in the sense that for a given input array, you have to create additional memory space proportion to the input size. So if you are given 100 elements to sort, you have to store those 100 elements as input. In addition to that, you have to create another 100 memory spaces for storing the integers. So that's not really acceptable in the sense that if your memory requirements or the space requirements grows with the input size, then the algorithm is said to be not in place. Okay? So you prefer the algorithm to be in place in the sense that the space requirement of the algorithm should not grow with the input size. If I want to sort 100 integers, I may need some temporary variables, like you might have seen your sorting algorithms before, some 2 or 3 temporary variables, or even like 10,000 temporary variables. But that temporary variables, the additional memory space I need, should not increase if I increase the input size. Okay, so that's when we say an algorithm is in place. Okay. Now, so that's why the time complexity as well as the space complexity of your algorithms are measured in terms of the input size. So typically, if you process an array, then it's measured as a function of the input array size, which is like n. So the time complexity could be n or n log n or n square and so on. But sometimes if your input is just one integer, for example, if you want to find whether a given integer is prime or not, then you just have one integer, then your input size is measured in terms of the number of bits that are needed to represent that integer. So which is typically given by 1 plus log n to the base 2 with floor. Okay, that's essentially because, for example, let me make it a little bigger. Okay. Yeah, so if you have 0, you need this one bit, which is 0, 1, you need one bit. If you have 2 represent 2, you need 2 bits, is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 1, 1, 0, 1, 1, 1, and 1, 0, 0, 1, so on. So up to 15, you can have, so that will be 1, 1, 1. So log of say 15 to the base 2 is going to be some 3 point something, and if you take a floor, that's going to be 3 and plus the 1, so that's why it is 4. Okay. Similarly, log say 2 to the base say some 5 is going to be some 2 point something. If you take a floor, it's going to be 2 plus 1, and that's going to be 3. Okay. All right, so how do we typically measure the running time of algorithms? For a given algorithm, it's very important we try to first find out what is the most time consuming operation that we do in the algorithm. And if we repeat that operation several times, we also need to find out how many times we repeat that most time consuming operation. So such an operation is called the basic operation. Okay? So essentially, the time complexity is nothing but a measure of how many times you execute the basic operation, and each time you execute the basic operation, how long it takes. Okay. So, for example, if you have the problem, like for example, if you want to do a sequential search, you're given an array, you want to find out whether a given key is in the array or not. The logic is essentially to, so for example, if you're given an array, um, say for example, you're given an array, say something like this, okay, and you want to find out whether a given element search key is in the array or not. What we will do is we will essentially search for that key in the array. We'll start with the first element and see whether the search key, for example, you're searching for 7. So we'll see whether the search key is equal to this element. If it is there, we'll just stop our searching and say the element is there. Okay. And we could also say this is at index 0. Array index starts from 0 to n minus 1, where n is the number of elements in the array. If it does not match, we'll go to the next element in the list and see if it matches. And we'll keep going until we either find a match or we hit the end of the array. If you reach the end of the array and say the element is not there, for example, you're searching for 1 and the element is not there, then you basically the element is not there, but you have done how many comparisons? We have compared the search key with this, the search key with this, search key with this, and so on. So we have made n number of comparisons, which is the n size of the array. Okay. So if on the other hand, if you get a hit, if you're searching for say 4 and you see it right there, with just one comparison, you're able to say it is there. So the basic operation here is the comparison. Okay, and the time complexity is basically a measure of how many times you have to do the comparison. Okay, and we just compare using the equal to operation, so that takes a particular time. So we'll focus more here on the number of times we do the basic operation, which is in this case comparison. So, so that's what it is. So, and it's not a constant. So the number of times you do the basic operation for this particular example is not a constant. It changes with, for your given particular array, it changes with the search key. Okay. So that's why it depends on the algorithm and what we want to do. The complexity will change with the basic operation. Okay. So for example, you get as of for given input size n, you get the different time complexity, which is nothing but now the number of times you can execute the basic operation to be something like this. This is the order actually in which the magnitude starts increasing. Okay, so log n, as n increases to infinity, log n is less than n. Is actually far less than n. As you can see the magnitude of the values, log n, and in this course we'll typically say log n to the base 2 or log n to the base e if I don't specify a base, okay, is always less than n. So since log n is less than n, okay, n is going to be less than n log n because you're adding a factor of log n to multiplying by n, as you can see here. To n, you're multiplying the log n factor, so n is going to be less than n log n. And since you have log n to be less than n, n times log n is going to be less than n squared. And that's what you see here. N times log n is going to be less than n squared. N squared is going to be less than n cube, and so on. And between the two, you should also notice that 2 to the n is going to be always growing less slower compared to n factorial. So actually, both these functions like 2 to the n or 3 to the n or anything or n factorial are not preferable time complexities. Okay, so but between the two, if you are to say which one's growing much faster, then n factorial is the one that grows much faster. Okay, so as we saw in that example of sequential search, we could have for a given problem and algorithm, there are three complexities. One is the best case complexity, the other is the worst case complexity, and the other is the average case complexity. So the best case is what's the minimum number of times you execute a basic operation as a function of the input n. Worst case is the maximum number of times, and the average case is on average how long we do. So for this example of sequential search, best case and worst case are quite easy to figure out. At the best, I can do just one comparison and say the element is there, or at the worst, I have to do n comparisons throughout the entire array, and the element is at the last element in the array or is not there in the array, then I would have to encounter n comparisons. Okay. Now the thing is, what is the average number of comparisons for this sequential search? Okay, and for this we need to understand a little bit about probability. So what we have here is a given array with n elements, and we're going to search for a key, right? Now, there is always a probability that the search key is going to be the array, okay? Because you cannot say whatever you're going to be searching for is in the array. There's always a probability that whatever you're going to search for is in the array, okay? So let P be the probability that for a given array, any particular search key is in the array. Okay. Now also the array is filled up with elements in a random order. So which means there's no specific order you filled up the array. Okay. Which means again what the search key could be at any position in the array. Okay. So if that is the case, the probability that the search key, there are n elements in the array, right? There are n elements in the array. So the probability that the search key could be at any particular index is 1 over n. Okay. But we also have something like what? There's a probability p that the key is in the array itself or not. Okay, so which means there is the probability that a given search key will be in a particular index in the array is p times 1 over n. Okay, so we can say that to be equal to p over n. Now, the search key could be at index 0, the first element, or the second element, the third element, and so on. So if it's the first element, we just do one comparison and say it is in the array. If it's the second element, we do two comparisons, right? If it's the third element, we do three comparisons and so on. So that's what I have here. The average number of comparisons is essentially, if it is the first element, we just do one comparison, and the search key could be the first element in the array with a probability p over n. If it's or, it could be the second element. So when you have probability and adding up for the average, you have to do a plus. So or it could be the second element. So if it's the second element, we do two comparisons, and it could be the probability p over n, again it's the second element, and so on. If it's the ith element, we have to do I comparisons, and it could be at the ith element with the probability p over n. Likewise, it could be if it's the nth element or the last element, we do n comparisons, and it could be there in the array with the probability in that particular position with the probability p over n. So all of this, or if the search key is in the array. Okay. So if the search key is not in the array, that happens with the probability 1 minus p. Okay, so the search key is not in the array, it happens with the probability 1 minus p. We have to do n comparisons and then find out that it is not in the array, right? So the average number of comparisons is essentially then the sum of all these things. The probability that the search key is in the array, and if it is in the array, at what position it is in the array. If it's not in the array, we will do n comparisons, and the probability of that happening is 1 minus p. So if you want to simplify this, essentially we have to, we can see that the p over n is a common term outside, and we can add up all these things. So it is 1 plus 2 plus so on up to I plus up to n plus n times 1 minus p. Now there's a formula for this. 1 plus 2 plus I up to n is n times n plus 1 over 2. And we have this p over n plus n times 1 minus p. So n and n cancels. So we can leave with this. Now we can try the two special cases. Say for example, p is 0. So what does that mean if p is 0? It is the probability that any search key is in the array is 0. So which means whatever you search for is not going to be in the array. So which means if you put p equals 0, this term goes to 0, and this is 1 minus 0 is 1 times n. So that shows you that if whatever you're going to search for is not in the array, then on average the number of comparisons you do is always n. So that's the worst case number of comparisons, because every time you input some key, it's not going to be in the array. Okay. On the other hand, if p is say 1, which means for a given array, whatever you're going to search for is guaranteed to be in the array, then if p equals 1, this term goes to 0, and this is 1 times n plus 1 over 2, which is simply n plus 1 over 2. So what we basically find out is, if the element is guaranteed to be in the array, then on average you do half, the number of comparisons you do is half the size of the array. Okay. And it makes sense, right? So if the element is in the array, you don't do always half the number of comparisons in the size of the array, but on average. So that's when when you do a simulation, you have a large array and you are trying to search for anything, and you're searching for something that is always in the array. Sometimes you may have 10 comparisons, sometimes you may have 70 comparisons, and so on. But on average, you search for several elements and then average out the number of comparisons you did. Then you'll find out the average number of comparisons you have is roughly approximately half the size of the array. Okay, we'll stop with this.